Once we're really comfortable with factoring, we can start to recognize the same structure in more complex factoring problems. We're going to use the exact same tricks we've used thus far, but we're going to see those tricks used with higher powers or higher exponents. The idea here is if I'm dealing with an even exponent on my variable, maybe y to the 4th, y to the 6th, or y to the 8th, we can think about that as another variable squared. Because if I pull the squared out of the exponent, it's like dividing the exponent by 2. So y to the 6th, for example, could be rewritten as y cubed squared. Or to make it easier, we just say that's x squared, and we work under the assumption that, talking about the second example here, x is equal to y cubed, so x squared is equal to y to the 6th. Similarly, above it, with y to the 4th, we say x is equal to half of that. X is equal to y squared. Then x squared would be equal to y to the 4th. Same thing with y to the 8th. We take half of that and say x is equal to half of that. So, get my pen back. X is equal to y to the 4th, then x squared would be double that, or x squared would be equal to y to the 8th. We can use a similar strategy with multiples of 3, and instead of doing halves, we do a third. So with y to the 6th, that's like y cubed squared. Y to the 9th is like y cubed cubed. Y to the 12th is y cubed to the 4th. And we can replace those with x cubed in much the same strategy. We take x and make it equal to y to 1/3 of the power. 1/3 of 6. 6 divided by 3 is 2. So that x cubed would be y to the 6th. With y to the 9th, we can say x is equal to y to 1/3 of the power. 9 divided by 3 is 3. Then x cubed is equal to y to the 6th, or y to the 9th, sorry. 3 times 3 is 9. With y to the 12th, we could say x is equal to y to the 1/3 of that power. 12 divided by 3 is 4. And then the x cubed would be equal to y to the 12th. In fact, this little trick doesn't have to just deal with one variable. It could be a group. Notice we've got y to the 5th squared. We could replace that with x squared. In other words, we say x is equal to the y plus 5. And then x squared would be all that stuff squared, y plus 5 squared. Making that simple substitution will take some advanced factoring problem and simplify it down to something we recognize and have factored before. Just add the extra step at the end that we put the original variables back, not the ones we made up. So that's right. Today, we're not doing regular factoring. We're doing advanced factoring. So let's take a look at some examples. Here I see that a to the 4th and a squared. We're not used to factoring with a to the 4th and a squared. We're used to dealing with x squared and x. So we're going to make x equal to half of that large exponent. X is equal to a squared. And then if I square both of those, x squared would be equal to a to the 4th power. Now, I can make a substitution. Instead of a to the 4th, that's equal to x squared. Minus 7, instead of a squared, that's equal to just x. Plus 12. And now that I've made my substitution, I say, hey, this we factored before. It's got 3 terms. X squared is x times x. 12 is 3 times 4. And if they're both negative, when we check that middle term, we'll find out we are now factored. However, we made up that variable x. X doesn't really exist. What really exists is a squared. X is equal to a squared. So we have to go back. Replace the x with a squared minus 3. Replace the x with a squared minus 4. And then what we'll do is we'll go back and say, okay, can this factor more? Each of these factors have two terms in them. A squared minus 3, we might think difference of squares, but I can't take the square root of 3. So there's really nothing I can do with a squared minus 3. However, a squared minus 4, that's a difference of squares with square roots of a and 2. We know that factors to a plus 2 times a minus 2. And we've taken this fourth power polynomial and factored it down to three factors of a squared minus 3, a plus 2, and a minus 2. Let's take a look at another example where we do this little substitution trick. 16 b to the fourth minus 1. We don't like dealing with b to the fourth, so we make x equal to half of that exponent, b squared. That way, when we double both exponents, x squared is equal to b to the fourth. We're ready to make a substitution. The b to the fourth is replaced with x squared, and we have 16x squared minus 1. Now we can factor this. Two terms. It's a difference of squares again. That's 4x and 1. So 4x plus 1 times 4x minus 1. We factored our difference of squares. However, don't forget to go back to the original variable. Go back to the b. So every x is equal to a b squared. So we have 4b squared plus 1. And 4b squared minus 1. Then to wrap it up, we make sure we can't factor these guys any further. 4b squared plus 1 is a sum of squares. Remember, a sum of squares does not factor anymore, so 4b squared plus 1 is all we have. But the subtraction does factor. That's a difference of squares again, with 2b and 1. So 2b plus 1, 2b minus 1. We have factored 16b to the fourth minus 1 down to 4b squared plus 1, 2b plus 1, 2b minus 1. One last example. By the way, I should also note that for this substitution step, you want to make sure you use a different variable. If the problem had x's in it, I wouldn't want to say x equals x squared. That's weird. I would make another variable, maybe z equals x squared. But here we have 8 times a plus 5 squared minus 14 times a plus 5 minus 15. And you'll notice that group of a plus 5 makes this feel weird and possibly difficult to factor. But if we make our new variable x equal to that group a plus 5, then when we square both sides, x squared is equal to the a plus 5 squared. Then we're ready to make our substitutions. 8 times a plus 5 squared, that's x squared, minus 14, a plus 5, we know that's x, minus 15. This is going to factor really nicely. A lot quicker than if I did all the work of multiplying out the a plus 5, distributing the 14, combining like terms. The numbers would get huge. It would be ugly. But this is not too bad. 8, that's probably 4x times 2x. Gonna have to do some guessing checks. We got a lot of possibilities here. 15 is probably 5 times 3. Let's see how we did on the outside. 4x times 3 is 12x. On the inside, 5 times 2 is 10x. That's 22x. That's not even close. Okay. Let's try switch the 5 and 3. Make it 3 and 5. Oh, I can put signs in here too. Let's make the first one negative and the last one positive, just because. 4x times 5 is 20x. 3 times 2x is minus 6x. That's a positive 14x. We're getting close. We want a negative 14x. So that just means our signs are wrong. It's going to be a plus and a minus. Plus and a minus. Now on the outside, we've got negative 20x. On the inside, 3 times 2 is 6x. That's negative 14x. That's what we want in the middle. We have now factored the green polynomial. However, we cannot forget to go back to the original. X equals a plus 5. So we have 4 times a plus 5 plus 3 times 2x, which is a plus 5 minus 5. Let's clean this up a little bit. Let me go back to blue to clean it up so we have a different color. Stay on the right slide here. 4a plus 20 plus 3 times, distribute the 2 through, 2a plus 10 minus 5. We've got some like terms to combine. 4a plus 23 times 2a plus 5. And we have factored that polynomial. So for these advanced factoring problems where we have higher exponents or groups, our strategy is by finding a substitution that makes life easy for us with x and x squared, or if the problem has x, use a different variable. We come up with something that's a lot easier to factor. And once it's factored, we can go back to the original variables. Don't forget to go back to the original variables. And then once you do, simplify that, and you will have factored by using the factoring structure underlying the problem. Good luck on the assignment tonight. Ask your instructor if you have any questions, and good luck to you.